yourselves. My name is Klebet Mukashanga, and welcome to our STEM in Action Grade 12 Boost series. And we're going to be looking at the topic electrostatics. So before we look at our topic today, we are going to look at some pre-knowledge material, which is material that you learned from grade 10. So the first thing that we're going to look at is charge quantization, and then charge conservation, electrostatic forces, vector addition, and perpendicular vectors. So on charge quantization, you would remember this image. It's an image of an atom. In this case, it's an image of a lithium atom. And if you look at it, you would remember that we have got the nucleus, which has got positively charged protons and also neutrally charged neutrons. And then we have got our electrons, which are negatively charged. And the charge of an electron is 1.6 times 10 to the power of negative 19 coulombs. So now imagine that we have got an object, and the object has got atoms, right? It's made up of atoms. It means that if we remove electrons from that object is going to gain a charge. If we remove electrons, that object is going to become positively charged. If we add the electrons to that object, it's going to become negatively charged. The charge that it gains is going to be a multiple of the charge of a single electron. So it means that Q, which is the charge that an object gains when it loses electrons or gains electrons, is going to be equal to N QE, right? Where QE is the charge of a single electron. So if we look at this object here, which is represented, we have got 16 positive charges and we have got 16 negative charges, so 16 electrons. If we remove 7 electrons from that object, we are going to get this object that still has 16 positive charges, but now has 90 negative charges. So to find the overall charge of this object, it means that we are going to use our formula and say Q is equal to NQE. And our N is 7 because N is the number of electrons that we have removed in this case. And we are going to multiply it by the charge of a single electron. And we will get this value. So if we look at this value, it is a positive value because in this case we removed electrons. So we are now ending up with more positive charges than negative charges. If we had added the electrons, we are going to put a negative charge there because our object was going to become negatively charged as a result. Charge conservation. So charge conservation simply says that if we have got a system, and let's say the system has various objects in it, we can transfer charges between the objects, individual objects in the system, without changing the overall charge of the system. So we can transfer charge from one object to the other, but the overall charge of the whole system does not change. So if we start with this object, with this image where we have two objects, and we have got those negative charges and positive charges on this object, and we have got the same scenario there. Both objects are neutral because they have equal number of negatives and positives. If we rub them together, what's going to happen is that we are going to transfer electrons from this object to that object. And this object is now going to be having a net negative charge of 2 because we transferred 2 electrons. And this one will have a net positive charge of 2 because we removed 2 electrons. But if we compare the overall charges in this first scenario versus the last one, we still have got the same overall charge of 0. So that is charge conservation. Electrostatic forces. So we know that when we have got a positive object and a negative object, the two objects are going to attract because unlike charges attract. But if we have like charges, either it be positive and positive, they are going to repel, or if it be negative and negative, they are also going to repel. Then vector addition, this you're already familiar with. So if we have got one force F1 with 3 newtons and an F2 with 7 newtons, and they are both pointing in the same direction, it means that our F net is going to be the summation of these two forces. And when we're adding them, we're going to say F net is equal to F1 plus F2. And because they are facing the same direction, it means that we are going to say plus 3 and plus 7. And we're adding the two forces. And we get our answer as 10 newtons to the right. However, if they are pointing in different directions, in this case, our 3 newtons is still pointing to the right, but our F2 7 newtons is now pointing to the left. It means that our F net is still going to be the summation of these two forces, and our formula is going to say F net is equal to F1 plus F2, but our F2 is negative, so it's now negative 7, and our F1 is still pointing to the right, so it is still positive 3. And our answer this time is going to be negative 4 newtons. And it is our force, the direction of our F net is to the left. Now, when our forces are at right angles, like in this case, so we've got our F1, which is pointing downwards, and our F2, which is pointing to the right. And our F net is going to be a vector that starts where F1 started and ends where F2 ended. So this is going to be our F net. And as we can see, we have got a right-angled triangle. And you would remember from your maths that we can use the Pythagoras theorem. So the Pythagoras theorem will suggest that we can say F net squared is going to be equal to F1 squared plus F2 squared. And we can put in our forces, and we know that we can rearrange this formula and say F net is equal to the square root of F1 squared plus F2 squared. And we can put in our values. Our F1 is 3 newtons, and our F2 is 7 newtons, and we'll get the answer from there. Now, if you want to find the angle here, we'll have to use trigonometric ratios. So we know that from this right-angled triangle, this side is going to be our opposite side because it is the opposite side to our angle. That's the adjacent, and the hypotenuse, the longest side on the triangle. And we get this formula which says that tan theta is equal to opposite of adjacent, and our opposite is the 7 newtons, and our adjacent is the 3 newtons. And from that, we can put this into our calculators. We don't necessarily need to write that down when we're working out our solution. And we'll get an answer, in this case, which is going to be theta is going to be 66.8 degrees. The Coulomb law states that the magnitude of the electrostatic force exerted by one point charge Q1 on another point charge Q2 is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance r between them. So if we have got two objects, in this case Q1 and Q2, and the distance between them is described as r, the formula that we get which describes the Coulomb law is going to be this formula. And in that formula, the F stands for the electrostatic force. So K is our constant, and K, the value of K, is going to be 9.0 times 10 to the power of 9 Newton meter squared per coulomb squared. And our charges are going to be here, Q1 and Q2, which is our particle charges, and this is the distance r between our charges. And please note that our force between our charges can either be an attraction force if the charges are unlike charges, but it is going to be a repulsion force if the charges are similar charges or like charges. So you also notice that we can compare the Coulomb law, which is the equation that we have just described, and the Newton's law of universal gravitation. And you can see that there are similarities between them. So the first one, as you can see, the F is a force, and Fg is also a force, and the K is a constant, and so is the G here. So our K constant is going to be this one, and the constant G value is going to be that one. And then we've got these two quantities, right? Where for the Coulomb law, it is the quantities or the magnitude of the charges. And for Newton's law of universal gravitation, it is going to be the mass of the individual objects that we are talking about, be it planets or otherwise. And then you have got the r squared, which is simply the distance between the charges for the Coulomb law, or the distance between the two objects or planets or whatever the case might be in the second law. So, to determine the direction of force when we have got two charges that are adjacent or close to each other, so you'd remember this formula that we have already introduced. So if we have got two objects, one that is positive and another one that is negative, what then happens is that Q1 experiences a force to the right. So Q1 is getting attracted by Q2, so it's going to experience a force to the right. And in your questions, you need to be able to identify the direction of the force, whether it be attraction or repulsion. So if you have got two objects in a question, you need to be able to identify the direction of the force that each object is experiencing, depending on whether it is being attracted to one side or being repulsed from the other side. And Q2 is going to experience a force to the left because it is being attracted to the left or being attracted to Q1. So in the second scenario, we have got like charges, and both charges are negative. We have Q1 and we have Q2. And what happens is that Q1 experiences a force to the left because it is being repelled by Q2, and Q2 experiences a force to the right because it is being repelled by Q1. When we have three objects, in this case we have Q1, Q2, and Q3, and if we consider the forces on the central charge, so in most of your questions, when we have three charges, usually the point that is going to be considered is the middle charge, right? So you will have to be able to explain the forces around the central charge. So in this case, the attractive force of Q1 on Q2 is to the left, right? So Q2 is experiencing an attractive force to the left, therefore it experiences a force to the left. And the attractive force of Q3 on Q2 is going to be to the right. So looking at this, it's a negative charge. It is surrounded by positive charges, so it's going to experience a force to the left because it's being attracted to the left. But at the same time, it's going to experience a force to the right because it is also being attracted to the right. This is a different scenario. We have got a positive charge surrounded by two charges that are dissimilar to itself, surrounded by a positive charge and a negative charge. And the forces that Q2 experiences, the first one is going to experience a repulsion force to the right. So repulsive force of Q1 on Q2 to the right. So Q2 is experiencing a repulsion force to the right because of the charge on Q1. Then at the same time, Q2 is experiencing a force to the right because it is being attracted to the Q3, which is of a unlike charge, right? So attractive force of Q3 on Q2 to the right. Now we can come and add our forces. So this is our image again from the previous slide, and we are just going to add our forces. So the forces that are being experienced by Q2, which is going to be our F net on Q2, is going to be equal to, we are adding this force, which is FQ1 Q2 plus FQ2 plus FQ3 Q2. And because if we consider our forces, we notice that FQ1 Q2 is going to the left, so it means that we are going to put it here as a negative if we are considering the right side as our positive direction. And FQ3 Q2 is going to be a positive because it is going to the right side. At the same time, if we consider our second scenario, the forces being experienced on Q2, again, we are saying F net Q2 is going to be equal to this addition of FQ1 Q2 plus FQ3 Q2. So in this case, because both our forces are facing in one direction to the right, which is the side that we have assigned the positive sign, it means that we are simply going to add them and both are going to be positive. When our forces or when our charges are at right angles, right? So here we have got Q 1 at the center, and we have got Q2 upwards and then Q3 to the right. The forces being experienced on Q1, so we know that Q1 is going to be attracted to Q2 because they have dissimilar charges or they have unlike charges, but it is going to be repelled by Q3, so it's going to be experiencing a force to the right. So the first one is going to be the force between Q1 and Q2, which, as we said, is going to be upwards. And then the second one is going to be the force between Q1 and Q3, which is going to be to the right. And our F net, we are going to use the parallelogram method. And our F net is going to be that line. And from that line, we can come up with our equation. So what you notice is that this force here, which is the FQ2 Q1, is the y-axis, right? So we can take it as the y-axis, and this one we can take it as the x-axis. And to resolve here, we're going to say F net is going to be equal to our FQ2 Q1 squared plus FQ3 Q1 squared, which is the formula that you are already familiar with, the Pythagoras formula. And from this, we can rearrange it to say F net is equal to square root of FQ2 Q1 squared plus FQ3 Q1 squared. And if you want to find the angle here, we will simply have to say the opposite over the adjacent. And our opposite is the same magnitude as this force. So we're simply taking that force and putting it as our numerator. And then we're taking the x component and we're putting it as our denominator into our tan theta equation to find this angle. This is the same if you are using a different method to find the same answer. But in this case, we still have this force which is going upwards, as we have already said, and we've got this force which is going to the right. But this time we are joining our resultant is a vector which joins from the beginning of the first force to the end of the second force, which is that one, and this is our angle theta. And likewise, our F net squared is going to be equal to our FQ2 Q1 squared plus our FQ2 Q1 squared, which is the Pythagoras formula. And we can rearrange it to that. And again, to find this angle, we are also going to say the opposite over the adjacent, like what we did already in the previous slide. Electric field. So electric field is a region of space in which an electric charge experiences a force. The direction of the electric field at a point is the direction that a positive test charge would move if placed at that point. So what we're simply saying is that if we have got charges, so we already established that charges can either be positive or negative or neutral. So to test whether a charge is positive or negative, we use a test charge. And the test charge is always a positive charge. And depending on which direction our test charge goes to, right? So we know that if it is a positive test charge, it is going to be attracted to the negative charge, but it is going to be repelled or move away from the positive charge. Therefore, we can use it as a test charge. So it means that if you have got two charges and you are not sure whether it's positive or negative, you use a test charge. If that test charge is attracted towards the charge that you are investigating, you can say that the charge that you are investigating is negative. If it moves away, it means that it is being repelled. You can say that that charge is positive. So in this case, this is a positive charge, that's a negative charge, and this is our test charge. And we can expect that our test charge is going to be moving away from the positive charge towards the negative charge. So we can draw up electric field patterns for a positive charge, and they're going to look like this. So basically, the electric field patterns are going to be moving away from the charge, right? So pushing away the test charge away from the charge. And you need to be able to draw these electric field patterns. And note that when you draw them, you use you identify your charge at the center, and you indicate whether it is positive or negative, and then you draw your lines using a ruler and a pencil, and make sure that your lines do not cross or do not intersect. So they have to look like that. And when it is the electric field pattern of a negative charge, we expect that our pattern is going to be having lines that are moving towards the charge, right? So it means that our test charge, which is positive, is going to be drawn towards our charge. Then we can have electric fields around two charges. In this case, if our charges are unlike charges, one positive and one negative, we still expect that our arrows are going to be moving away from the positive charge towards the negative charge and be able to draw these patterns. If the charges are like charges, whether they are both positive or they are both negative, our lines are going to be moving. In this case, they are going to be moving away from the positive charges in both cases, and you get this type of a pattern. And if this was negative and negative, you would get the same pattern. The only difference would be that our lines were going to be moving towards and also moving towards. And now I'm going to do a simulation to portray this concept. So in our first simulation, I have clicked here to show the electric field, and we have got our positive charge, our negative charge, and this is going to be acting as our test charge, which we said is positive. So I'm going to put in here the positive, and you can see that our electric field lines are moving away from the positive charge. And I'm going to put in a negative, and you can see that our electric field lines are moving towards the negative. If I put a sensor in between, the red line is showing the direction that our sensor is being pulled towards or away from. And you notice that our sensor is pointing to the right, so it is being pulled towards the negative charge. And the closer it gets, the stronger that pull gets, right? So as we decrease the distance between them, our force is going to be increasing, like that. And likewise, as I push it closer to the positive charge, the repulsion force is also going to be increasing. But what I want you to notice here is that the arrow is representing the direction of the force that it is experiencing. And we are noticing that when it is close to the positive charge, it is experiencing a repulsion force, which is moving away from the positive charge. When you move it towards the negative charge, it is experiencing an attraction force, which is moving towards the negative charge. So the electric field E at a point is the electrostatic force F experienced per unit positive charge, Q, placed at that point. Or we can say it is the force per unit charge. So it is simply how much force is being experienced per given amount of charge, right? And we can come up with a formula for that, which says E is equal to F over Q, where that is the force and Q is the charge of that point or at that point. So this is an image that we have already talked about. And we are saying that if we have got a positive charge and we have got a test charge, we already said that the test charge experiences a repulsion force away, which forces it, or the direction of the force is going to be moving away from the positive charge. Therefore, test charge Q experiences a force due to the electric field surrounding Q. And the magnitude of the electric field E at a point can be expressed as this, right? So we are saying the magnitude of the force that this point is experiencing as a result of the charge on Q here can be expressed or found by saying E is equal to F over Q, where Q is the charge of that point. And we can rearrange this formula to say F is equal to QE. And if we take it further, so in this case, we still have got our positive charge, and this is our point that we are interested in. And this is the distance between our positive charge and the point that we are interested in. And we can now rewrite this. We already expressed this formula as saying F is equal to QE, and we already know that F is also equal to KQ1 Q2 over R squared, where Q1 is going to be perhaps the charge here, and Q2 will be the charge of that point, and R is the distance between them. Therefore, we can say that because we have got F and F here, we can equate this part, and we say QE is going to be equal to KQ1 Q2 over R squared. And therefore, we can rearrange this by taking the Q to this side, and we put the Q there. And when we have this formula, we can say that the Q, the capital Q, is representing the charge at the positive charge, and then the small q is representing the charge of the point that we are talking about, or our test charge, or whatever point, if it has got a charge on it. But what you notice is that we now have got a small q on the numerator and a small q on the denominator, so we can cancel those out, and we get this as our final equation. And what this simply says E is equal to KQ over R squared. So it means that if you want to find the electric field at a point, which is a distance R from a charge, we simply need to multiply the K, which is our constant, times the charge of that point over the distance between the charge and the point that you are interested in. Therefore, keeping this equation in mind, so to find out the electric field on a point using that equation, if we have got two charges, right, a Q1 and a Q2, where Q1 is positive and Q2 is negative, you would remember that the electric field surrounding a positive charge is going to be moving away from the positive charge, but moving towards a negative charge. Therefore, the electric field that this point experiences as a result of the charge on Q1 is going to be a push to the right. But at the same time, because it is being pulled towards the negative charge, Q2, we are also going to experience an electric field to the right. And the summation of the electric field that this point is experiencing can be found by adding this electric field, which is EQ1, plus this electric field, which is EQ2, because the electric field is a vector. So we can add them the same way that we add vectors. Here we've got a different scenario where our charges are like charges, and what we expect is that our point here is going to experience a force to the right, because we know that positive charge emits a force away from itself, but it's also going to experience a force to the left, because we have a positive charge here, and it is the electric field is also moving away from it. So it means that when we add up our vectors, we are going to say E net is going to be equal to EQ1, which is that one, plus EQ2. But our EQ2 is a negative because it is going, its direction is to the left. Therefore, it means that our E net final equation is going to say positive EQ1 plus negative EQ2. If our electric field points are at right angles to each other, in this case, we have got a positive charge here and a negative charge there, and this is our point of interest. And what do we know? We know that the electric field around a positive charge move away from it. So it means that this point experiences a downward force because of this charge. And we know that the electric field lines around a negative charge, they move towards the negative charge. Therefore, this point is going to experience an electric field to the right as a result of this charge. Our E net is going to start from, so we are adding it the same way that we add vectors, and our first vector started from there to that point, and our second vector started from there to that point. So we are just connecting the beginning of vector 1 to the end of vector 2, and that is going to be our E net. And to find the E net, we apply the Pythagoras theorem, which says that E net squared is going to be equal to EQ1 squared plus EQ2 squared, and we can rearrange this formula to that to get our E net. And to find the angle theta here, again, we apply the trigonometric ratio, which says opposite over adjacent. So this is our opposite, which is our x component in this case. So that becomes our numerator, and the y component in this case becomes our denominator. So we're going to look at some application questions. And our first question is going to be paper 1 November 2017, question 7. It says two small spheres, x and y, carrying charges of positive 6 times 10 to the power of negative 6 coulombs and positive 8 times 10 to the power of negative 6 coulombs respectively, are placed 0.2 meters apart in air. And I would like here to just mention that before you apply your formula or your answer, make sure that the units are in the correct SI units. So your charges should always be in coulombs. So if it says NC, it means that you need to convert it. And your distance should always be in meters. If it is in any other unit, make sure that you convert it first to meters. All right, so this is our diagram. And 7.1 says state Coulomb's law in words. The Coulomb's law says the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance r between them. Then our question 7.2 says calculate the magnitude of the electrostatic force experienced by charged sphere X, right? So I'm simply going to, so 7.2 says calculate the magnitude of the electrostatic force experienced by charged sphere X. So I'm just going to draw our scenario. This is point X, this is point Y, and our charge on X, positive 6 times 10 to the power of negative 6 coulombs, and our charge on Y, positive 8 times 10 to the power of negative 6 coulombs. And firstly, I'll have you notice that our charges are both positive, so it means that the force between these two charges is going to be a repulsion force. And the question is asking us to find the magnitude of the force, the magnitude of the electrostatic force experienced by charge Q. And I'm going to indicate here that it's going to experience a force to the left as a result of the repulsion that it is getting from charge Y. And our formula says force is equal to K Q1 Q2 over R squared. So on our diagram, I'm going to indicate our distance, which is our R, as 0.2 meters. And so here I'm simply going to rewrite this formula and replace Q1 with QZ, with QX, because this is charge QX, and replace Q2 with QY, because this is charge Y, over R squared. And then we're going to put in our values. So our K is a constant, and the value is 9 times 10 to the power of 9. Qx is this charge, 6 times 10 to the power of negative 6. Qy is that charge, 8 times 10 to the power of negative 6. Our R is 0.2 squared. So our final answer is going to be 10,8 newtons. So this is our diagram, and we have introduced a third charge, which is Z, and we were told that that charge is a negative charge. We know that this is a positive charge, and we know that this is also a positive charge. And the question is asking us to draw, draw a vector diagram showing the direction of the electrostatic forces and the net force experienced by the charged sphere Y. So we are interested in the forces that are being experienced by Y, as a result of the charge on X and as a result of the charge on Z. All right. So if we look at our charges, we know that Y is positive. So if I identify this point, and I'm going to say this is my point Y, and we are going to draw the forces that Y is experiencing. We are going to start with the force on Y from X. And we know that these are like charges. They are both positive. It means that Y is experiencing a repulsion force to the right. So we can say Y is experiencing a repulsion force to the right, and we identify our force as force XY because it is force from X on Y. So we know that our Y is a positive charge and our Z is a negative charge. Therefore, what is the direction of the force that Y is going to experience as a result of the charge on Z? And we know that Y is going to be attracted towards Z because they are unlike charges. It means, therefore, that Y experiences a downward force towards Z because of that attraction. And we are going to call this FZY because that is the force that Y is experiencing as a result of the charge on Z. So once we have done that and we have identified, we can describe this as our X component and this as our Y component. Our resultant, which is our F net, is going to come there. 7.4 says the magnitude of the net electrostatic force experienced by charged sphere Y is 15.20 newtons. Calculate the charge on charge Z. Right, so we have our formula, which is going to say, so we've identified Fxy and Fzy and our F net. So our formula is going to say F net, we're applying the Pythagoras formula, is F, the X component, Xy squared, plus Fzy squared. And we are told here that the F net is actually 15.20. And we have already calculated our Fxy, and we already found it out to be 10.8. And this is what we are looking for. I'm going to say Fzy squared. So we can simply rearrange this and say that 15.20 squared minus 10.8 squared is going to be equal to our Fzy squared. And we'll say Fzy is going to be equal to the square root of 15.20 squared minus 10.8 squared. So our final answer for Fzy is going to be equal to 10.696 newtons. But we are not yet done, so we still need to find the charge on sphere Z. Right? So we come back to our original formula for force, which says that F is equal to K Q1 Q2 over R squared. And I'm just going to rewrite this and say F is equal to K. In this case, we're interested in the charge QY. So I'm going to say here QY and the charge QZ, which is Z, over R squared. So firstly, I'll just rearrange this to make QZ subject of the formula. So we're going to say we multiply both sides by R squared. So we have got F times R squared is equal to K QY QZ. Then I'm going to divide both sides by K QY so that we can cancel this one, we cancel that one, we cancel that, we cancel that, and we remain with our what we are looking for on that side. And we are saying QZ. We already know that our force is 10,696 newtons. So here 10,696 newtons. And our distance is 0.3 meters, and we need to square that. Our K is 9 times 10 to the power of 9. And our QY is already given as 8 times 10 to the power of negative 6 coulombs. And our final answer is going to be 1.34 times 10 to the power of negative 5 coulombs. There's our final answer. The next question is paper 1, March 2018, question 8. So P is a point 0,5 meters from charged sphere A. The electric field at P is 3 times 10 to the power of 7 Newton per Coulomb, directed towards A, referring to the diagram below. So this is our diagram, and what we have here is we have got our charge point A, and P is a point which is 0,5 meters away from our charge at A. 8.1, draw the electric field pattern due to charged sphere A. Indicate the sign of the charge on the sphere in your diagram. So, looking at our diagram, we are told that the electric field at P is that value directed towards A. So the fact that our electric field is going towards A tells us that the charge on A is a negative charge. So if you do remember when we talked about directions of electric fields, depending on if it is a positive charge, it's going to be moving away from the positive charge. If it's a negative charge, it's moving towards the positive charge. So this here is what tells us that the charge on A is a negative charge. Therefore, to draw our forces, I'm just going to do that, put our negative charge. And again, you make sure that your lines do not cross or touch each other. 8.2 says calculate the magnitude of the charge on sphere A. Right? So we know that we have got our formula which says that E is equal to KQ over R squared. And we know that our K is 9 times 10 to the power of 9, and our charge is 3 times 10 to the power of 7 over the distance, which is 0,5 meters, and we need to square that. And our answer will come out as 8,33 times 10 to the power of negative 4 coulombs. 8.3. Another charged sphere B having an excess of 10 to the power of 5 electrons is now placed on point P. Calculate the electrostatic force experienced by sphere B. So in this case, this is still our point A, but we now have got a point B. The distance between them. So in our second scenario, we still have got sphere A here, and we have replaced our position P. We have now put on position P a sphere B, and that sphere B has got a charge as a result of an excess of 10 to the power of 5 electrons. So we need to find firstly the charge on sphere B. So if we have got an excess of 10 to the power of 5 electrons on sphere B, to find the charge on sphere B, we apply our formula for quantization of charge, right? And it says Q is equal to N QE, where N is the number of electrons and QE is the charge on a single electron. So it's going to be Q is equal to N is 10 to the power of 5, and our QE, we know that it is 1.6 times 10 to the power of negative 19 coulombs, and we are going to get a charge of 1.6 times 10 to the power of negative 14 coulombs. And once we have done that, we can now calculate the electrostatic force experienced by sphere B by applying our force formula, which says F is equal to K Q1 Q2 over R squared, and I'm just going to rewrite it and say F is equal to K QA QB over R squared, and we're going to put in our values. We know that K is 9 times 10 to the power of 9. QA, you are already given that as 3 times 10 to the power of 7. And QB, we have already calculated that as 1.6 times 10 to the power of negative 14. And our distance between them is 0.5, and we need to square that. And if we do that, we are going to get an answer of 4.8 times 10 to the power of negative 7 newtons, and it is going to be a force to the right. Because our sphere A, we already identified it as negative, and our sphere B is going to be negative because there's an excess of electrons, so it's going to be negative. So there's going to be a repulsion force between them, which means that sphere B is going to be getting pushed to the right as a result of the charge on sphere A. So our final answer is going to be 4.8 times 10 to the power of negative 7 newtons to the right. So this marks the end of our session on electrostatics.